Hi everyone, welcome to Integral Calculus. Today we explore lesson 9.3, applications of separable differential equation. First example, under ideal condition, population grows at a rate proportional to the size of the population. Model the population growth. We did this in section 9.1. What we're gonna do today is we're gonna figure out a model for the population PT. We can solve for this differential equation because it is a separable differential equation. dp over p is k dt. Integrate both sides, and we have ln p equal kt plus c. Take e as base, then we have p equal ekt times e to the power c. Well, e to the c is just another constant, and therefore pt is ce kt. Ah, what a nice model. We usually solve c using initial condition. And we can solve for k using another condition. Example 2, Newton's law of cooling states that the rate at which the temperature of an object changes is proportional to the difference between the temperature of the object and the surrounding temperature. Express this law as a differential equation. We did this in section 9.1. What we're going to do today is figure out a model for the temperature of the object, T of T. Because there is a differential equation, a separable one, we can solve for T. dt over T minus Ts equal K dt. Integrate both sides, and we have ln absolute value T minus Ts equal Kt plus C. Now that E has the base, and we would have T minus Ts. We don't need absolute value because the exponential function is positive. E to the Kt times E to the C. Well, E to the C is just another constant, meaning that T minus Ts is Ce Kt, and therefore T of T is Ts plus Ce Kt. Oh, this is cool. Similarly, we can find C using an initial condition. And we can solve for K using another condition. Last example, mixture. A tank initially holds 300 gallons of mixture, both water and salt. We pump in both water and salt at a rate of 3 gallons per minute with salt concentration of 2 pounds per gallon. Then we well stir well mix before pumping out at a rate of 3 gallons per minute. Model the rate of salt in the tank at time t. So in section 9.1, we let A of t to be the amount of salt at time t. Then the rate of salt in the tank at time t is dA over dt, and that is the input rate of salt minus the output rate of salt. Input rate of salt is the inflow concentration of salt multiplied to the input rate, which is 2 pounds per gallon times 3 gallons per minute. Output rate of salt is the outflow concentration of salt multiplied to the output rate, Well, the outflow concentration of salt is 80. We have no idea the amount of salt, but then we know the amount, the total is 300. So 80 divided by 300 pound per gallon. The output rate is 3 gallons per minute. And therefore, we have a differential equation. dA over dt is 6 minus 80 over 100. Now we can solve for the amount of salt at time t. This is a separable differential equation because we can make it so. dA over dt is 600 minus 80 over 100. And so dA over 600 minus 80 equal to 1 over 100 dt. Integrate both sides, and we have minus ln absolute value 600 minus 80 equal 1 over 100 t plus c. So take E as the base. But before that, I'm going to move the exponent -1 up there. Or I can divide both sides by -1. So ln 600 minus 80 equal -1 over 100 t minus c. Now we can take E as the base on both sides. We have 600 minus 80 equal e to the -1 over 100 t times e to the -c. Well, from here, we can see that a of t is 600 minus c e to the -1 over 100 t. Very nice model. And we can figure out c given an initial condition. Thank you for watching. I hope you found the content useful. Please like, subscribe to help the channel growth. I'll see you in the next video.